is for the mean, not the mean, what is extreme value theorem. There's a different one, but we use the extreme value theorem. So this was the last section we covered, and it really ties in everything, almost everything we've done, partial derivatives and such. So I've got this template developed that will help you see all the steps involved. Yes, it's many. Again, I encourage you to use this template to kind of work through the problems from the homework as well, and the practice questions. So I'm going to take a stab here at question number 19. I have not worked this in advance, so let's see how this goes. So we come over and we're going to write our objective function, which is given to us here. And remember, this extreme value theorem basically states as long as we've got a continuous function and we have a closed bounded domain, which that's what the constraints tell us, that x is bigger than 0, bigger than or equal to 0, but less than or equal to 4. That should be an x in the middle, not a 0. Okay, there we go. And then that y, let me do that one first, is between 5 and 0. That's what that's saying. Okay, so it fits the extreme value theorem. And what it tells us is we will have a maximum and a minimum. Could be more, but we will have a max and a min. Actually, we'll have an absolute min and an absolute max. We could have some relatives in there that are also max and mins, but we'll only have, as we know, we only can have one absolute. There can only be one biggest of the big. So how do we go about? So one of the first things we want to do is sketch the bounded region and then shade the feasible region. So I'll do that in, we'll do it in yellow. Yeah, why not? So x goes from 0 to 4. So here's 0 to 4. That's your x value. See if that, I don't know if that comes out very good, but well, let's go in blue then. Okay, so we're going to go from 4. Y is going to go all the way up to 5, so we know we got a horizontal line here. So we can just draw that on a graph, and then we're x is bigger than 0, so there's a boundary here, a boundary there. Let me go with the red for the corner points. That gives us some corner points here and here, here and here. And of course we got all along the boundary. And remember, this function is some kind of three-dimensional shape that is now bounded by this, so it's hard to visualize, and we don't have to, but there's a lot going on in there. Let me just maybe shade it in yellow. That will, so I will shade in the feasible region like this. Okay, so be able to do that so you can kind of see what's going on. And what that will help us with is, okay, one of the first things we want to get is we want to list the corner points from the constraints. And most of the ones we're dealing are have rectangular corners. So we see the point 0, 0 here. So this is almost, once we draw it, it's by inspection. We see the point 4, 0, x is 4, y is 0. And I'm not listing them in any particular order. We get the point 0, 5, so x is 0, y is 5. And then we get the point 4, 5. So those are our corner points. And potentially they're the places where a max or a min could occur, because those are on the boundary. So we took care of those. Those are our candidate points, right? And then what we're going to do is we're going to plug each of these into this function up here and get their values. I'll do the 0, 0 first, so 0, 0, 0, 0. So that's the easiest one to find. We're going to get a z value of 0. So that's a potential. Right now it's the maximum and the minimum, because it's the only value we found so far. Put in 4, 0, 0, 5, and But what I want to do is I want to kind of get the points first, so we kind of get this flow, and then we'll come back and we'll just evaluate each of these points in this function to get all the z values, and then we'll be able to tell which value is the biggest and which one's the smallest. So the next step, now that we've got our corner points, is to list the critical points that lie within the region, in the interior. So that would be in this yellow shaded region. So there could be some in there, and they would occur wherever the partial derivatives equal 0. So what we're going to do is come back up here. We're going to take our function. We're going to get its partial derivative, set the partial derivatives, and set them equal to 0. Now we don't have to figure out whether they're max or mins or anything. We are going to do that later, but we just need to find where is the partial derivatives of this, where are they equal to 0. So actually this is not, I might have to adjust this. This really should be like the partial is equal to 0, not the function equal to 0. So don't want to throw anyone off. I'll fix that on my template before I post it. All right. So let's see. Let's take our function, and that's why I'm using Word. Oh, that's right. I forgot about that. Well, I can do it over here. I got lots of scratch work area. So we're going to take our function. I want to take the derivative with respect to x. So for x is 1, the derivative. So 4 times 1 is 4. Come to 6y. Y is a constant. The derivative is 0, taking the derivative with respect to x. Come to x, negative x squared. The 2 comes down, so that's going to give us 2x to the first. So we get a minus 2x squared. And the last term, y squared, since y is a constant in this sitting, the derivative would be 0. So there's our partial with respect to x. We'll set that equal to 0 and solve it, but while we're at it, let's keep taking derivatives. So the derivative, the partial derivative with respect to y, come along. For x is, well, it's a constant, so that derivative is 0. Come to 6y. We take the derivative of y, which is 1. 1 times 6 is 6. We take the derivative of x squared. X is a constant, so x squared is a constant. Its derivative is 0. And now we come to y squared. Y is a variable. Derivative of y squared is going to be minus 2y to the first power. Okay, so we're going to set each of these equal to 0 and solve. I see. I need you all here so you can catch when I do things. Sometimes I can catch them myself sometimes, but it's always nice you guys can see these things. So yeah, it's minus 2x, not minus 2x squared. Just, but you know, sometimes as you're looking over these, you might find yourself making these kind of errors. I tend to as well. To this day, I've got over 40 years of college level math, 5 years as an undergraduate student. Yes, it did take me 5 years to get through, and a couple of years as a graduate student, and about 25 years as a teacher. So, okay, this is going to be easier. So we set, let me get my pen back. We set this equal to 0. When I saw the square, that was so yeah, we just set this equal to 0, add 2x to both sides. That gives us 4 equals 2x, right? That cancels out. Divide both sides by 2, and we get x equals 2. And then over here, this is nice. I'm just going to cheat a little bit. I'll just let it equal to 0. Add 2y to both sides, and then you get 6 plus 0 equals 2y, positive 2y, because you added it to both sides, right? And then we divide both sides by 2, and we get that y equals 3. So that's one potential possibility, the point 23. So we come over here, and we fill that in. And if you want, you could label it, this is an interior. I'll do that. And then these from here, let's do this. These are our corner points. corner points. And then now what we're going to get down here, I don't know how many we're going to have, but potentially we could have 4, but sometimes we're going to see when we go for these boundary lines, right, that we don't get a point that's usable. We don't get a point where the partial derivatives are equal to 0. Okay, so sheet, but it doesn't take care of that. So anyway, so that was the B part. C part, we're going to get the critical points on the boundary with xy subject to the constraints. Okay, so here's how that works, is we take our function, f of x, and we're going to plug in a constraint. So one constraint on this boundary is the vertical line. So one constraint really is these equal places. So x equals 0. That's a vertical line. That's this vertical line here. I guess maybe I could label it down here if I wanted to. And then I'm going to get the other vertical line of x equals 4. So what I do is I plug those into x. That really makes it a constant. And then I take its partials, right? So my new function with the constraint, let's do this, f0y. Do this one constraint. Okay, well, let me do this. This is 4 times 0 plus 6y minus 0 squared. So you can see exactly what I'm doing. So 4 times 0 is 0. So we get 6y. This is 0 minus y squared. Okay, so that's our new function. What we want to do is take partial derivatives of this new function, because this is going to give us along the boundary. Well, hopefully you can see that the partials with respect to x, that's just going to be 0, because when we take the partial with respect to x, y is our constant, so that's 0. When is that 0? It's 0. So 0, 0, but I guess we've already got that point, right? Then we take the partial with respect to y, and we get 6y. Its partial would be, the derivative of y is 1, so that's 6. Derivative of y squared is going to be minus 2y to the first. And again, what we do is we set this equal to 0, kind of like what we did before, right? And add 2y to both sides. Divide both sides by 2. So you get 3 is what y is. And then what we do is if we plug in 3 for y, sorry, I forget mixed up here. We already know that x is 0. Okay, that's what we've plugged in. That's all x can be, because we're on this vertical line. All x could be is 0. So that gives us the point 0.03. Okay. We don't have it listed, so let's go ahead and list it. Okay, so that was taking that constraint. Let's take the other constraint when x is 4, y. So we're going to go ahead and go through that one. So 4 times 4, we're plugging that in, minus 6y minus 4 squared minus y squared. Okay, and then we get 4 times 4 is 16 minus 6y. 4 squared is 16 minus y squared. 16 minus 16 is 0, so those are gone anyway. They would have dried up when we did the derivative anyway. So again, we would, so it's again 6y minus y squared. Kind of a boring number that keeps coming up. So let's take the partial with respect to x. We'll do that real quick. There is no x's, so the derivative with respect to x is going to be 0. And then the derivative with respect to y, we have a negative 6y. Uh-oh, where'd that negative 6y come from? My imagination. Oh, how did I do that? Okay, but I didn't do it too much. Okay, I must have been looking ahead. Sorry, it's positive 6y. So derivative of y is 1. 1 times 6 is 6. Come to negative y squared. The 2 comes down. Minus 2y to the first power. We're going to set that equal to 0. We're going to add 2y to both sides. That gives us 6 plus 0 equals positive 2y, because positive 2y plus 0 is 2y. Divide both sides by 2. So we get y equals 3. What is 4? Well, it's, what is x? X is 4. See, I think backwards. So 4, 3 is a potential. It's a candidate. 4, 3. Sometimes it's just so confusing when your mind, I don't know why some things just don't want to erase. But it's kind of like the real world, right? So we'll make this into a 4, this into a 0. Let's cross that out. This into a 4, and this into a 3. So there's another point. I want that one. This is 3, and this is 3. Okay, 4, 3, and make it prettier later. Okay, and then now I do the same thing with the y values. Y could be 0, so this is this line down, this horizontal line is y equals 0. This horizontal line up here is y equals 5. So we plug those in and we do the same thing. So maybe I'll do that up here. So I'm going to plug in f of x comma 0, plugging in 0 for y. That's going to give us 4x. I'm over here just recopying this down, plus 6 times 0 minus x squared minus 0 squared. So if we get 4x minus x, right, this is 0, that's 0, minus x squared, sorry. So that's our function. So we can take the partial with respect to x, and that gives us 4 times 1 minus 2x. Partial with respect to y is just going to be 0 because that's all, there is no y, so that's a constant. Set the partial equal to 0. 4 minus 2x equals 0. Add 2x to both sides. 4 minus 2x. Divide both sides by 2. X equals 2. What is y? Y was 0. So we get the point 2, 0. Okay. We'll do the same thing with y equals 5. Let me maybe come over here. So f of x comma 5. And you'll kind of see it's going to be really the same thing because you're plugging in the constant, right? 4x plus 6 times 5. And when we take its derivative, the constant becomes 0 anyway. So it doesn't really matter. This is going to be 25. This is going to be 30. But when you take their derivatives, constants, their derivatives are 0. So we get this function, same thing. And I'll get a little sloppy. I'll just call it f. 4x minus x, and we know when we take the derivative with respect to x, we're going to get 4 minus 2x. When we set it equal to 0, it's the same thing we get here. We're going to get x equals 2 and y is equal to 5. Remember, the partial with respect to y would be 0 because there is no y in this function here. So it's a constant. It's just 0. So we get 1 point, the point 2, 5. So you could label those, right? 2, 5. Let's see. Do it this way. 2, 5 is a potential for, it might be a maximum in there. 2, 0 is a potential. So, you know, maybe, remember we've got some kind of a surface that could be 4, 3. 4, 3 is also potential right here in the middle. And 0, 3. is another potential point for a maximum. And then in the interior, 2, 3, 2, 3. That could be. So maybe they're all going, I don't know what it really looks like, but that might be the maximum. So those are all the points we came up with. They're all potentially, and so maximums or minimums. One will be an absolute max and one will be an absolute min. And the way we find that now, so we did that, is this last step. We're going to evaluate the function at each of these points. So we're going to get all the z values. The biggest z value, that's our maximum. The smallest z value will be our minimum. So it's kind of tedious, but what we're going to do is we plug in 4 for x and 0 for y. Now, one of the biggest things is make sure you're using the right function. You use the original objective function. Well, yeah, we don't come and use any of these other ones, these partials or whatever we've been doing. Those only give us the critical points. What we're wanting now is the z values. Okay, so we're going to plug in 4. So I'm going to just kind of do that as scratch work. 4 times 4 is 16. We're plugging in 0 for y, so that's gone, and then we've got minus 4 squared. 4 squared is 16. Well, that's going to be 0. Okay, so this one gives us a z value of 0. 0, 5. So x is 0. Those go away. 4 times 0, this. So I've got 6 times 5. That's going to give me 30. I guess maybe I should do this. I was evaluating for 0, and that gave me 0. Now we're going to evaluate 0, 5. And I'm going to get 30, and then I put in here minus 5 squared is 25. Wow, I got something other than 0. I got 5. So this value is 5. We're going to evaluate the point 4, 5. F of 4, 5. So we plug in 4. 4 times 4 is 16. 6 times 5 is 30. Minus x squared. X squared was 4, so that's minus 16. And then minus 5 squared, which is minus 25. 16 minus 16 is 0. 30 minus 25, that leaves us with 5. So far, 5 is the max. And it's occurring at 2 points, but we'll see what we get. Plugging in 2 and 3. Okay, so maybe we'll get something different here. I don't know why some things go away and some things don't. Some things will erase. Well, it was a free app, so maybe that's it. Cancel that out. So we'll look at f of 2, 3. So we'll go through this. 4 times 2 is 8, plus 6 times 3. 6 times 3 is 18. Minus 2 squared. 2 squared is 4, so that's a minus 4. We're going to get something different. And minus y squared. Y squared is 3, so that gives us minus 9. And let's see if we can do the math. We got 8 and 18. That should be 26. Do it along the way. Subtract 4 is 22. Subtract 9 is going to be 11. No. 2 and then 7, 13. Let's check it out with a calculator just to be sure. So you get 8 plus 18 minus 4 minus 9. 13, yeah. Okay, I thought that's what we were at. Okay. That's that one. And then now we've got these boundary points. So we've got 0, 3. So we'll do that. F of 0, comma 3. And again, we're back up here. 4 times 0 is 0. 6 times 3 is 18. 0 squared is 0. And then 3 squared is 9. So that gives us a 9. Okay, so far, the 0.23 is our maximum, right? It's the biggest value so far. Let's keep going. 4,3 is a potential, so we go with f of 4,3. And we know when we plug in 4 for x, we're going to get 16, positive 16. Plug in 3 for y, we're going to get 18. X squared, 4 squared is 16, so we get a minus 16, so those guys kind of cancel each other out. And then we get a minus 3 squared, which is 9. So 18 minus 9, we also get 9. And so that, it's kind of a surface, seems like, maybe going down, maybe, wait, actually, what is this? 2, 3 is up at 13, so that's the high point. These are a little bit lower down. Let's see what happens. We got 2, 0 and 2, 5 left. So f of 2, 0. What's going on? Where did those come from? Oh yeah, we used the boundary. We got 2 both times. Okay, 2 comma 0. And so we plug in 2 for x. 2 times 4 is 8. 0 for y. That's going to be 0. We're plugging in 2 for x, so that's minus 2 squared is 4. So minus 4. And then we plug in 0 for y, so that's 0. So we get the value of 4. So this one's 4. And then we plug in 2, 5. So 2 for x, that gives us 2 for x, 4 times 2 is going to give us 8. 6 times 5 is going to give us 30. 2 squared is 4, so that's minus 4. And then 5 squared is 25, so that's minus 25. Looks like we get, that's going to give us 34 minus 25. 34 minus 25 is 9. Double check that. Yeah, 9. Okay. So this one's 9. So we do have a maximum. Absolute maximum. I guess I should change colors, right? Here's our maximum. And it looks like we've got 2 potential minimums on these corner points. And so we would list our minimums as 0, 0, 0, and 4, 0, 0, and our maximum should be just this one, 2, 3, 13. Let's go ahead and take a look at the answers. This was number 19. Because I didn't work this in advance. Oh, that's not, I don't have it here. Let's see if I've got it open. Let's see, 19. Okay, it's kind of a mess here. Let's see, come over here. Absolute maximum value of f, the function is equal to 13, occurs at 2, 3. Absolute minimum of f equals 0 occurs at these 2 points. Okay, so that's good. We all our points that we found are all listed. They didn't do a sketch, but we did a sketch. So I just want to make sure that I didn't make some funky calculation error here. But we could list it as triplets. It just depends on how they want them. You know, we could list the function values. But notice, while there's 2 points where the absolute minimum occurs, there is actually only one absolute minimum, which is the minimum value of 0, but it happens to occur at 2 points. Okay, so this is sort of our final answer, because they said well, what was the question? Find the maximum, absolute maximum, and absolute minimum. That's all we were asked to do to find these points. Look at all that was involved in getting there. All right, so those, again, let me know about this template if you have some ideas that might work better, but give it a try. Either have it to the side and go through, but that's the process you got to go through. Get the corner points, get the interior points, get the boundary points, find all the z values. The biggest one is your max, and the smallest one, that's your min. All right, thank you guys, and we'll keep moving forward.